two projects. In this video, we are going to explain the project Proposal of SVM Utility Kernel for Breast Cancer Survival Estimation. Introduction. This project combines qualitative histological data with quantitative genomic insights to improve breast cancer prognosis and diagnosis, aiming for more accurate and timely predictions of clinical outcomes. Due to breast cancer's global impact as a leading cause of cancer related deaths, there is an urgent need for enhanced tools to predict survival and reduce overtreatment. The project addresses this need by refining the approach to breast cancer prognosis. The project benefits patients and oncologists by providing a reliable tool for predicting breast cancer survival. Accurate prognosis helps tailor treatments, minimizing risks and optimizing healthcare resources. Using machine learning techniques and big data analysis, the project developed survival prediction models. Data from sources like Metabrick and the Cancer Genome Atlas are utilized, marking a significant step forward in addressing breast cancer complexities and predicting varied clinical outcomes. Objective of the project. So, as I mentioned earlier, this project aims to alleviate the challenges faced by oncologists in cancer prognosis, particularly focusing on the intricate nature of breast cancer across various modalities. The goal is to improve survival prediction for breast cancer by introducing a utility kernel for support vector machines, that is SVM. This kernel proves effective, particularly in scenarios involving small and imbalanced datasets. And we aim to validate the proposed utility kernel's efficacy through comprehensive testing across gene expression, copy number variation, clinical, and histopathological image modalities. The objective is to demonstrate its superiority over advanced deep neural networks in handling challenging aspects of breast cancer data. Requirements needed to execute this project are: software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are: operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working modules of law of work. So the first step is import and required packages. So in this step we import essential Python libraries like pandas, numpy, sklearn, TensorFlow with keras, matplotlib and seaborn. These packages are fundamental for data manipulation, machine learning and visualization tasks. The second step is data pre-processing. So the data pre-processing phase involves tasks like appending utility kernel and PCA feature values, subsampling long data, and generating balanced class data for training. It ensures that the data is in a suitable format for subsequent analysis. The third step is exploring the dataset. Here we delve into the dataset, examining various modalities such as clinical data, that is CLN, whole slide images, that is WSI, gene expression data, that is EXP, and copy number variation, that is CNV. Understanding these components is crucial for developing accurate survival prediction models. The next step is combining the data. Here, data integration is performed by combining different modalities such as CLN with EXP, that is clinical and gene expression, CLN combined with CNV, that is clinical and copy number variation, CLN combined with WSI, that is clinical and whole slide images, a multimodal combination of WSI, CLN, CNV, and EXP, etc. These integration enhances the robustness of the models. The next step is visualization using Seaborn and Matplotlib. In this step, we employ Seaborn and Matplotlib to create visual charts and graphs, facilitating a better understanding of dataset characteristics. The next step is splitting the data to train and test. In this step, we segregate the dataset into training and testing subsets. The training subset is used for model learning, while the testing subset evaluates the model's performance on new data. The next step is training and building the model. Here, we'll train various survival prediction models using machine learning algorithms such as SVM, random forest, decision tree, naive Bayes, and deep learning architectures like VGG nets, rest nets, and dense nets. And the models are applied to predict 5 to 9 years of survival for breast cancer patients based on different modalities. For each time point, survival prediction models are developed individually for all the combination of data sources. And in the next step, that is extension phase, a hybrid model was created by combining predictions from multiple models for improved accuracy. Additionally, a user-friendly Flask-based frontend with authentication was developed. The next step is Flask framework with SQLite for sign up and sign in. In this step, we integrate user registration and login functionalities into the Flask framework. Users can sign up by providing their information and subsequently they can securely log in using their credentials. This enhances system security and allows for personalized user experiences. So, after signing in, users provide input through the front-end interface. The input data is pre-processed to prepare it for prediction by the trained models. This pre-processing step ensures that the user provided data is in a suitable format for the model. And the pre-processed user input is fed into the trained models for prediction. The best performing model is selected to make predictions based on the input data, and the predicted outcome is displayed through the front-end interface, allowing the user to view the results of the model's predictions or analysis. Now we'll understand about the algorithms used. So first we have built support vector machines, that is SVMs. So SVMs are pivotal in our breast cancer survival prediction project. Leveraging SVM kernels like radial basis function, that is RBF, polynomial, utility kernel, linear and sigmoid, these models find optimal hyperplanes to separate data into classes. The RBF captures intricate nonlinear relationships. The polynomial adapts to diverse nonlinear patterns. The utility kernel aligns with breast cancer intricacies. The linear suits linearly separable data, and the sigmoid handles nonlinear separations. SVM's flexibility with nonlinear relationships and effectiveness with small, high dimensional datasets make them powerful tools for breast cancer survival prediction. The next algorithm built is random forest. So, random forest is an ensemble learning method that constructs a multitude of decision trees during training. It combines their predictions to improve accuracy and control overfitting. In this project, it aids in creating robust survival prediction models. The next one is decision tree. So decision trees are simple yet interpretable models that make decisions based on feature values. While prone to overfitting, they are valuable for understanding feature importance and contribute to the ensemble learning approach. The next algorithm used is Nye-Bayes. So Nye-Bayes is a probabilistic classification algorithm based on Bayes' theorem. Despite its assumption of feature independence, it is efficient for text classification and high-dimensional data, providing a probabilistic framework for breast cancer survival prediction. And we have used VGG nets, REST nets, and dense nets, renowned for image classification. They were adapted to process and extract features from combined genomic, clinical, and histopathological datasets in our breast cancer survival prediction project. Despite their complex architectures, we sought their versatility across various data modalities to capture intricate patterns, enhancing the project's comprehensive predictive capabilities. So, here is a graph illustrating survival prediction models at 5-year survival, incorporating different dataset combinations and algorithms. So, the model names are overlapping due to the variety of algorithms used. So this is the horizontal bar graph comparing accuracies of all the algorithms. In this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. So similarly we can see accuracy score comparison graphs for survival prediction model at 6, 7, 8 and 9 years survival in these slides. So the algorithm which is best performing will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is data folder in which I have clinical, whole slide image, gene expression and copy number variation datasets along with class 5 year, class 6 year and other files which are used for training models to predict breast cancer survival at 5, 6, 7, 8 and 9 years. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. And these are Jupyter source files, which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. So now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if you are new users, we have to register first. Fill in all these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password and click on login. So it has redirected us to the detection page. So now we have to fill in these parameters and click on predict button to get the detections. So these features comprise clinical information, gene expression values, copy number variation data, and histopathological whole slide image features from breast cancer patients. So now we'll enter these parameters. So feature 1 would be 0.51, feature 2 would be 0.41, feature 3 is 0.3, feature 4 would be 0, feature 5 would be 0.5, feature 6 is 0.13, feature 7 would be 0.28, feature 8 is 0, feature 9 is 1, feature 10 would be 1. Now click on predict button. So here we can see the outcome, that is the patient is diagnosed with breast cancer based on features given. We'll try again. Click on home link. We'll try giving another set of parameters. This time feature 1 would be 0.20, feature 2 is 0.42, feature 3 would be 0.33, feature 4 would be 0.06, feature 5 is 0.5, feature 6 is 0.14, feature 7 would be 0.28, feature 8 is 0, feature 9 would be 1, and feature 10 is 1. Now click on predict button. So here we can see the outcome, that is the patient is not diagnosed with breast cancer based on the given features. So similarly, we can give any set of parameters and can get the detections. Now click on sign out. So the conclusion here is the project systematically assessed various machine learning algorithms, including SVMs with diverse kernels, traditional methods, and deep learning architectures like VGG nets and ResNets. The introduction of a utility kernel tailored for breast cancer survival prediction within SVMs demonstrated promising results, emphasizing the significance of customized algorithms. The project integrated clinical data, whole slide images, gene expression, and copy number variation datasets for a comprehensive approach, leveraging diverse information sources. The project's extension efforts include exploring a voting classifier which has demonstrated promising results. This addition enhances the predictive capabilities, underscoring the project's commitment to refining breast cancer survival predictions through innovative approaches. And the implementation includes a Flask based deployment showcasing the practical application of the developed algorithms in a user friendly web interface for wider accessibility and usability. And the project provides valuable insights into algorithmic suitability for breast cancer survival prediction, emphasizing customization and versatility for accurate predictions in medical contexts.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.